Many functions can be written in terms of a power series. We can think of a power series as an infinite polynomial. A power series takes the form of the sum from k equals 0 to infinity of a sub k times the difference of x and x sub 0 to the power of k, where all of the a's and x sub 0 are constants. We can think of a sub k as the formula that gives us the coefficients, and we say the power series is centered at x sub 0. Recall x sub 0 would give us a shift left or right. If we expand the power series, we have a sub 0 plus a sub 1 times the difference of x and x sub 0 plus a sub 2 times the square of the difference of x and x sub 0 plus a sub 3 times the cube of the difference of x and x sub 0, and so on. To get a better feel for this, let's look at an example. Let's consider the power series the sum from k equals 0 to infinity of negative 1 to the power of k times x to the power of the quantity 2k plus 1 divided by the quantity 2k plus 1 factorial. Notice for this power series, a sub k, the formula that gives us the coefficients, is negative 1 to the power of k divided by the quantity 2k plus 1 factorial. Also notice because we have x to the power of the quantity 2k plus 1, x sub 0 is 0, which indicates the power series is centered at x equals 0. This power series converges for all values of x, indicating the interval of convergence is from negative infinity to positive infinity. We'll talk more about the interval of convergence in a few minutes, but to determine the interval of convergence, we typically use the ratio test or root test shown here on the right. Now going back to our power series, let's find the first several terms. The power series is equal to x minus 1 divided by 3 factorial x cubed plus 1 divided by 5 factorial x to the fifth minus 1 divided by 7 factorial times x to the seventh, and so on. This is the power series for sine x. And again, this converges to sine x for all values of x. To get a better idea of this, let's take a look at the graph of the power series as we add more and more terms and see how it converges to the graph of sine x. If we graph just one term of the power series for sine x, we have this line. And again, as we add more and more terms to the power series, we can see the power series converges to sine x. Here's a list of power series for several common functions. When the power series is centered at x equals 0, they're often called Maclaurin series. On the far right, we have the interval of convergence as well as the radius of convergence. The radius of convergence can be found by starting at the center of the power series and determining the distance to one of the endpoints. And now let's take a look at a few power series and determine the interval of convergence as well as the radius of convergence. For the first power series, we have the sum from k equals 0 to infinity of 1 divided by k factorial times x to the power of k, which I've expanded on the right. We're asked to determine the interval of convergence and the radius of convergence. Well, first notice because we have just x to the power of k, the power series is centered at x equals 0. And now to determine the interval of convergence, we'll go ahead and apply the ratio test shown here on the right. The root test is also a common test used to determine the interval of convergence, which means in our case, we need to find the limit as k approaches infinity of the absolute value of c sub k plus 1 divided by c sub k, where c sub k is a formula used to determine the terms in the power series, where c sub k in this case is 1 divided by k factorial times x to the power of k, or if we want, which we see here at the bottom, x to the power of k divided by k factorial. And to find c sub k plus 1, we replace k with k plus 1, which gives us on top x to the power of k plus 1 divided by the quantity k plus 1 factorial. To simplify the complex fraction, recall dividing by a fraction is equivalent to multiplying by the reciprocal, which means we can take the top fraction and multiply by the reciprocal of the bottom fraction, indicating we multiply by k factorial divided by x to the power of k. And now if we focus on the factorials, recall that k plus 1 factorial is equal to k plus 1 times k minus 1, and so on. K plus 1 factorial is equal to k plus 1 times k factorial. The k factorials simplify out, leaving us with 1 divided by the quantity k plus 1. Now looking at the x's, x to the power of k plus 1 has one more factor of x than x to the power of k, and therefore x to the power of k plus 1 divided by x to the power of k simplifies to one factor of x. And now determining the limit, as k approaches infinity, 1 divided by the quantity k plus 1 approaches 0, and therefore the limit is equal to 0. And recall, when applying the ratio test, if the limit is less than 1, then the series converges. Well, 0 is always less than 1, and therefore the power series always converges, which indicates the power series converges for all values of x, and therefore the interval of convergence is from negative infinity to positive infinity. This also indicates the radius of convergence is infinity. If we take a look at the graph of the interval of convergence, we would graph all real numbers on the number line, and because the graph is centered at 0, 0 moving all the way to the right or to the left indicates the radius of convergence is infinity. Let's take a look at a second example. This power series looks similar, but now we have 1 divided by k, not 1 divided by k factorial. Again, we will use the ratio test to determine the interval of convergence and radius of convergence, which again means we need to find the limit as k approaches infinity of the absolute value of c sub k plus 1 divided by c sub k, where c sub k plus 1 is x to the power of k plus 1 divided by k plus 1, and c sub k is x to the power of k divided by k. Again, to simplify, we multiply by the reciprocal of the fraction on the bottom, and now we try to simplify. K divided by k plus 1 doesn't simplify, and x to the power of k plus 1 divided by x to the power of k simplifies to 1 factor of x. And now determining the limit as k approaches infinity of k divided by the quantity k plus 1 approaches 1, and therefore the limit is equal to 1 times the absolute value of x. And recall, this only converges when the limit is less than 1, which means to determine the interval of convergence, we need to solve the equation, the absolute value of x less than 1, which indicates x is less than 1 and x is greater than negative 1. So now we know the power series converges on the open interval from negative 1 to positive 1, but whenever we determine the interval of convergence, we need to test to see whether the power series converges at the endpoints. So now we need to test for convergence at x equals negative 1 and x equals positive 1. So at x equals negative 1, if we substitute negative 1 for x in the original formula for the power series, we have the sum from k equals 1 to infinity of negative 1 to the power of k divided by k. You may recognize this as the alternating harmonic series. If we apply the alternating series test, we will see this converges at x equals negative 1. And now we test x equals positive 1, which gives us the sum from k equals 1 to infinity of 1 to the power of k divided by k, which is just the harmonic series, which we should remember diverges by the p-series test with p equals 1. The power series converges at x equals negative 1, but diverges at x equals 1, and therefore the interval of convergence is the interval from negative 1 to 1, where the interval is closed on negative 1 and open on positive 1. Because the power series is centered at x equals 0, from 0 to 1 or from 0 to negative 1 is 1 unit, indicating the radius of convergence is 1. Before we look at the third possible outcome, when determining the interval of convergence and radius of convergence of a power series, I wanted to look at the previous example again when the power series is not centered at 0. Notice in this case, because we have x minus 2 to the power of k, x sub 0 is 2, indicating the power series is centered at x equals 2. We still determine the interval of convergence using either the ratio or root test. Again, using the ratio test, here's the setup. Again, this is just like the last example, except instead of x, we have the quantity x minus 2. Simplifying, we end up with the limit as k approaches infinity of k divided by the quantity k plus 1 times 1 factor of x minus 2. And since the limit as k approaches infinity of k divided by the quantity k plus 1 is 1, the limit is equal to the absolute value of x minus 2, which must be less than 1 to converge. Which means to find the interval of convergence here, we now need to solve this absolute value inequality, which indicates x is less than 3 and x is greater than 1. And therefore the interval converges over the open interval from 1 to 3. And again, testing the endpoints, we test x equals 1 and x equals 3. On the left endpoint, the series converges. On the right endpoint, the series diverges. And therefore the interval of convergence is the interval from 1 to 3, closed on 1, open on 3, and the radius of convergence is still 1. So notice how it simply shifted the interval of convergence 2 units to the right, because for this example, the power series is centered at x equals 2. And now let's take a look at our last example. We have the sum from k equals 0 to infinity of k factorial times x to the power of k. Again, applying the ratio test, we have the limit as k approaches infinity of the absolute value of c sub k plus 1, which is k plus 1 factorial times x to the power of k plus 1, divided by c sub k, which is k factorial times x to the power of k. Simplifying, we have the limit as k approaches infinity of k plus 1 times x, but the limit as k approaches infinity of k plus 1 approaches infinity, and therefore the limit approaches infinity, which is always greater than 1, which indicates the power series diverges, except where it's centered, in this case, x equals 0. So we can say the power series converges only at x equals 0, and therefore the radius of convergence is 0. We have just seen the three types of outcomes when determining the interval of convergence. Number 1, a power series converges for all x. Number 2, a power series diverges, except at x equals x sub 0 where it's centered. And number 3, there is an interval of convergence determined by the ratio or root test. Just remember the endpoints must be tested separately. I hope you found this helpful.